Hi, I am Yupeng Liang. I will present our work Multimodal Material Segmentation. We aim to realize accurate material segmentation, for example, dense per-pixel material recognition, particularly for road scenes. We propose multimodal material segmentation using polarization consisting of angle of polarization and degree of polarization and near-infrared images. We introduce a new dataset and a novel network for this multimodal material segmentation task. We built a multimodal imaging system that consists of a stereo pair of RGB polarization cameras, an NIR camera between them, and a LiDAR below the three cameras, all mounted on a push card roughly at the head of the hood of a car. The stereo and LiDAR help propagate material annotations across all imaging modalities and viewpoints. Our M-Cubes dataset consists of two distinct types of image sequences. The first type of sequences are captured while the imaging system continuously moves forward. The second is the panning sequences. M-Cubes dataset consists of 42 scenes of the first type with 424 image sets and 19 different scenes of the second type. The total number of annotated image sets is 500. We define 20 material classes by carefully examining these real-world road scenes, which can be classified into 5 groups: pavement, vehicles, human, nature, and others. We annotated the left RGB image for each pixel and propagate all labels to other modalities. We introduce a novel deep neural network, M-CubesNet, to fully leverage the multimodal material appearances. M-CubesNet uses deep lattice replace as the backbone encoder to extract multimodal low-level and high-level features. These encoded features are then filtered with a novel region-guided feature selection convolution layer. Material occurrences are strongly correlated with object instances. We leverage this rich interdependence between objects and materials by using object categories as priors on material segmentation. The idea is to learn different convolutional filters to apply to each semantic region. A naive implementation of this idea, guided dynamic filter, incurs too much computational cost. Also, some material appear in multiple semantic regions. Simply learn a filter for each semantic region will ruin the underlying connection. Our key idea is to learn an over-complete set of convolutional filters across the entire image. Also, learn to assign different sets of those filters to each semantic region. For the semantic guidance, we use deep lattice replace for this, which is applied to the input RGB image outside the M-CubesNet. We consolidate the semantic classes of cityscapes down to 10 classes. They are road, human, car, bicycle, building, wall, bridge, pole, terrain, and nature. When consolidating classes, we focus on the consistency of materials in each semantic class. This image shows the details of our RGFS call. First, the input feature passes through regular convolution to generate the intermediate features. The number of filters is controlled by a hyperparameter lambda. K refers to the number of output channels of RGFS call. Semantic segmentation results are used as the guided field. The intermediate feature is divided into semantic regions. Next, in each semantic region, we compute the average response R of each of the regular filters. Then, in each semantic region, we select the filters with the K largest average responses. The filter results become the output of RGFS call. In the absence of other multimodal material segmentation methods, we compare our methods with multimodal semantic segmentation network and 2 dynamic filter methods. We also add the semantic guidance to these 2 dynamic filter methods. Overall, our M-CubesNet performs better in recognizing the road and can discern the real track from its surrounding concrete. Also, we investigate how each imaging modality contributes to the per-pixel recognition of different materials. Polarization adds significant information to achieve higher accuracy, especially for discerning metal and dielectrics. And NIR helps accurately recognize water in the river and some wet surfaces. Also, AOLP alone helps discriminate asphalt from other road materials. The combination of the AOLP and NIR also adds to recognize the concrete. As a conclusion, we introduce our work M-Cubes dataset and design a M-CubesNet which can fully leverage 4 imaging modalities to realize multimodal material segmentation. We believe M-Cubes dataset and M-CubesNet provides a sound platform for exploring multimodal material segmentation. Thank you.